Hello everybody, this is Tommy, and today we're going to be going over explainer problem number 2, and it asks, how does a refrigerator appear to get around the second law of thermodynamics? Thermal energy is only supposed to flow from hot objects to cold objects. How does a refrigerator take thermal energy out of a cold object? How is a refrigerator uh, different from a heat engine in reverse? What constraints to the second law of thermodynamics put on the temperature ranges of the system relative to the temperature of the cold reservoir and the temperature of the hot reservoir? Where is the work being done in the refrigerator, and be sure to include a PV diagram. So the PV diagram I got is just one of the first search results on Google when you search up PV diagram for a refrigerator, and it matches my explanation pretty well. Oops, I accidentally drew a line there. So if we start out at a point, just say this point right here, that's going to correspond to this point in the diagram. So inside of these squiggly lines, or like what they're supposed to represent tubes, there's going to be a coolant solution, and at the current point, the coolant solution is going to be first of all highly pressurized, a liquid, and at normal temperature. So once it enters this expander right here, the pressure will drop and the temperature will decrease, and since the pressure is dropped, the boiling point will now be much lower. So part of that coolant solution is now going to be vapor exiting the expander. And you can see that in the PV diagram. As you can see, the pressure definitely takes a drop and the temperature drops too. So after it exits the expander, it will go through the evaporator tube, and because it is now lower temperature than the inside of the refrigerator, it will now absorb the heat from the inside of the refrigerator to contribute to the vaporization process. So at the end of the tube, before it reaches the compressor, it is now going to be all vapor because it took the energy or the heat energy from the inside of the refrigerator. It kept so that's how it keeps all of your food cool. It just absorbs the heat energy from the inside of the refrigerator. It's still going from a warmer place to a colder place, so the second law of thermodynamics is not violated in this point. And at the end of it, it's going to be all vapor now. Right before it gets compressed, it's going to be at about this point in the diagram. So what the compressor does is that it puts work on what is now the vapor of the coolant. So it essentially just, if you want to imagine it, imagine like a gas getting squished together. The pressure is now much higher, and because it got compressed, the temperature is higher too. So outside of this, so right outside of the compressor, we have a very pressurized gas that's also very hot. But in order to restart the cycle, recall that we need a liquid coolant that is normal temperature, and but is also still pressurized. So in order to get rid of the excess heat, the heat is just thrown out into like the surrounding environment. So that's why it's warm at the back of your refrigerator. So this really hot, highly pressurized gas is allowed to cool down, and as it travels up the condenser tube, it becomes liquid again, and then by the point that it reaches, right before it reaches the expander, it's going to be the highly pressurized coolant, liquid coolant at normal temperature again, and that's how it works. As you can see here, during this process where it outputs the heat energy into the environment, it's still moving from a hot place to a cold place. So throughout the entire system, none of these processes violate the second law of thermodynamics. So and that's where, and yeah, so that's why it doesn't violate the second law. And where the work is being put in is in the compressor, where it just squishes the gas so that it becomes highly pressurized. And yeah, that's going to be it for my explanation. Thank you.